I think I can start by introducing Volker. So it's really a great pleasure to welcome Volker as our first Quid Ultra colloquium speaker in 2022. And so thank you, first of all, for accepting our invitation. And Volker is a Josie Centennial Professor in Astronomy at the University of Texas at Austin. He is the chair of the Department of Astronomy since 2019. And Volker received his PhD from Yale University in 2000 with a thesis on star formation in the early universe. And the thesis was recognized with a Robert Templer Award of the Astronomical Society of the Pacific. And after postdoctoral fellowships at Cambridge University and Harvard, he joined the faculty of astronomy at UT Austin in 2004. And Volker is an internationally recognized leader in the theoretical understanding of the early stages of cosmic history. And he has pioneered the theory of formation of the first stars, the first black holes, the assembly of the first galaxies, investigating their physical properties and exploring their impact on the overall evolution of the universe, from reionization to 21 centimeter signals to the unresolved infrared background. And with his group, Volker has published very influential papers in this field. He has written reviews which really stand as reference points for the field. And in addition to this outstanding scientific activity and institutional duties, Volker is also very engaged in several outreach programs, writing popular articles, appearing in TV documentaries, and he provided some of the science visualizations for the Tree of Life movie, which won the Palme d'Or at Cannes and was nominated for the Academy Awards in the Best Picture category. And in preparation of the discovery potential of the James Webb Space Telescope, today Volker will share with us his view on what we know about the first stars and galaxies. So thank you, Volker, for accepting our invitation, and I leave the floor to you.
Thank you, Rafaela, for this very kind introduction. And let me say that I am really honored to have the chance to speak in this series today. And Quid Ultra, of course, this is what a wonderful title for this series: Frontiers and Controversies in Astrophysics. But for the subject today, my hope is that this is mostly about frontiers, the frontier of when we push our attempt to understand the first stars and galaxies to the very beginning, the first few 100 million years after the Big Bang. So this will be a talk very much in the spirit of Quid Ultra, the frontiers of what we know about the early universe. And to begin, the big picture, there's really a beautiful story that cosmology, astrophysics, our field has been able to put together over the last century. Almost we begin with the inflationary fireball, and now we know that the quantum processes in the ultra early universe imprinted the seeds for all of the cosmic evolution that is then to follow. And we also know then that 14 billion years later we end up with a universe that is incredibly complex, highly structured, full of interesting things for us to discover. But then we have come to understand that a few 100 million years after the Big Bang, what is sometimes called the cosmic dark ages, we have this important transition from the simple initial conditions of the early universe to this unfolding complexity. And of course, the first few 100 million years, when the first stars, galaxies, black holes formed, the first supernova exploded, gamma rebirths. All of this at this point is largely still beyond our current horizon of observational cosmology. So of course, the high redshift frontier is a moving target. So here I just schematically picked a billion years, but of course we know that we can push with frontier observations, the Hubble, the the large telescopes, VLT, Keck, and so on, a little bit further back. So we have some previews in what is out there. But of course, you also know that we are just at the threshold for really getting a tremendously expanded view of the early universe with frontier telescopes. Of course, the James Webb Space Telescope has been launched, but also then the extremely large telescopes that will be built, that are being built on the ground, the European mission, the GMT, TMT in the Americas. So all of this is happening. So we are just at this incredibly exciting point where we push the frontier, and we really can then see how star and galaxy formation first got going. And from the theory viewpoint, right, our field has put together, I believe, also an incredibly beautiful standard model of first star and galaxy formation, because when we push star and galaxy formation to the very beginning, we get into a realm of, in a way, in a manner of speaking, great simplicity. And we know all the ingredients in principle, right? We know we have the standard model of cosmology, lambda cold dark matter, lambda CDM. We know the dynamics of the expanding universe. We know with incredible high precision from the cosmic microwave observations, the matter energy content of the universe, and crucially, very important in particular for theory, for cosmological simulations, we know our initial conditions imprinted by the early universe as visible in the large scale structure and the fluctuations in the cosmic microwave background. And then for the first stars and galaxies, the first baryonic objects, we also deal with the most primitive, most simple baryonic situation. We have the primordial gas, hydrogen, helium, and very simple molecules, mostly molecular hydrogen. And in principle, we have all the processes in terms of chemistry of destruction, formation, and the important cooling processes. And then also just to mention this, it's really always good to remember the cooling function of primordial gas. So the cooling rate is a function of temperature, which is really, when we think of how this looks in the present day interstellar medium, all the processes that contribute to cooling, heating of the interstellar medium, this is incredibly complicated, complex, right? Fills an entire book, and thousands of papers have been written on the ISM cooling and heating. But for the primordial gas, we have a very, very simple situation. There basically are only two ingredients. This red line is the contribution from atomic hydrogen, and atomic hydrogen is a very, very strong coolant. And sort of this peak here is, for example, Lyman alpha cooling. Right, we excite atomic gas, and then we can cool it by emitting Lyman alpha photons. So this is very strong, but the problem is that this is only effective at high temperatures, so temperatures in excess of 10,000 Kelvin. So this is really where molecular hydrogen cooling comes in, because if you want to form something interesting, stars, population 3 stars, the first stars, we need to cool to lower temperatures in the realm of 1,000 Kelvin and below, and then we really have to rely on molecular hydrogen cooling. So really, this is a situation of great simplicity. And to just maybe phrase this in one more conceptual way, when we think about this idea that we want to understand star formation and galaxy formation really in the early universe, then we know the cosmological initial conditions. And at some point we can think about this schematically as a kind of a black box where we have inputs, and the inputs are the parameters of cosmology as measured to extremely high precision by the CMB missions. Then right in the black box, of course, we have the laws of nature. And in principle, for our problem, first star, first galaxies, we can write them all down in a compact way. And then we have to get supercomputers to work because even the simple laws very quickly lead to great complexity. But then if we put this together, then we have outputs. So we start with microscopic, microphysical inputs, and then we get these macroscopical, astrophysical, cosmological outputs, the properties of stellar systems, the stellar initial mass function, star formation efficiency, multiplicity, binarity, right, whatever we are interested in. And the interesting thing is, of course, at some point, logically or conceptually, we can run this from left to right, right, input, output. There's, of course, also then causality, but very importantly, right, as astrophysicists, astronomers, we can turn this around. We can start with these macroscopical observables, which we can observe and which we will observe with ever higher precision and degree of detail. And then we can turn this around, and then we can basically go back to the inputs. And if you think about the inputs, although we know, right, the cosmological parameters very well, there's at least, right, one extremely important part of the picture that we do not have a very good understanding of, and this is the microphysical nature of the particle physical nature of dark matter. Right, we cannot at all be sure of what this dark matter is. I believe at a recent conference which brought together cosmologists, astrophysicists, and fundamental physicists, then sort of there was particle physicists, and there was sort of this picture that dark matter, right, we see it on the sky everywhere. Right? We cannot really construct understand the universe without invoking dark matter, but then the particle physicists in their earthbound laboratories, detection experiments, colliders, don't see any hint beyond the standard model. So this is a real problem. But then really, when we think about this, we can use astrophysics as a laboratory, right, to constrain the particle physics nature of dark matter, and we will get back to that later. But so all in all, really conceptually, when we are contemplating the beginning of star and galaxy formation, yeah, there's great beauty, and it's just incredibly exciting. And of course, as we said, we are just about to confront our theoretical picture with these new frontier telescopes from the JWST and other missions. So just to remind us what we have learned, many of us, Rafaela's group has contributed to this picture greatly in many ways as well, but really it's a community effort. So for the last 20 years or so, right, many groups have worked on this, different numerical approaches, and we have seen the emergence of a standard model of how the first stars formed. And there are some aspects that are universally agreed on, understood, and then there are things where we don't agree at, where we are at the frontier. So just to start with the aspects of population tree star formation where we all agree. So a cosmological box, gravity organizes the cosmic matter into the famous cosmic web, filaments, and where the filaments intersect, we have regions of high density where the action in terms of forming interesting things, star formation, galaxy formation, black hole formation first starts. And then if we put together this combination of cold dark matter, lambda cold dark matter, and primordial gas, then very robustly we identify mini halo, a million solar mass, dark matter and gas objects, redshifts 20 or 30 or so, where star formation first started. And then these mini halos, we also all agree on, all methods agree on that if one zooms in, one gets to a stage where for the first time, when we reach this gas clouds of maybe a few hundred solar masses, extensions of a parsec or so, we reach a state for the first time in the history of the universe where the gas, the baryonic components, becomes self-gravitating, decouples from the dark matter. So everything is driven by dark matter until this point. But now we have this object, we could call this in analogy to the language of present-day star formation, if you like, a pre-stellar core. So again, masses of a few hundred solar masses, the size of a parsec. This is the first self-gravitating gas cloud in the universe, and this is the immediate progenitor for forming stars. So we have decoupled from the dark matter, and then if we go with a higher resolution and see what happens in this Jeans unstable, gravitationally unstable, collapsing pre-stellar core, then the second piece of the picture emerges that also is robust. Then at some point in the very center of a mini halo, if one really goes with very high resolution, then right, one can resolve a protostellar disk. There's a disk. The disk is gravitationally unstable. There's the formation of an initial population 3 protostar, and then because the disk is growing so quickly in terms of dumping a huge amount of primordial gas onto the disk, then this disk is very rapidly driven to further instability, and then there are formation of further protostars. So the picture is that very rapidly we have the formation of a protostellar system, a small multiple population 3 multiple forms. That is also agreed. Now we come to the frontier. The frontier has really two aspects. The first frontier is that it gets really incredibly messy very quickly when we think about what happens inside this mini halo when we study the evolution of these protostellar disks. And this is a movie that was made, now it's 10 years ago, by Thomas Greif, and many of us still remember him. He has done beautiful work in this field, and this is sort of one of his most beautiful visualizations that he contributed to the field. So this is Thomas Greif's picture of how this dynamics of there's this initial protostar unfolds, and this is formally temperature. So you see there's cooling, shocks, and all of this leads to secondary formation, further fragments, but then there's a huge degree of viscosity in the disk. And then, although we constantly form new fragments, we also merge them. So there's this intricate dance of merging and survival. And just if you look at this plot here and just sort of focus on the right side, this shows the rate per year of the black line shows new fragments. So early on, a large amount of new fragments form, and then this rate of new fragment formation drops down. But then, very interestingly, there's also, this is sort of this red line, you can barely see it, but sort of it's almost on top of it of merging fragments, and this is almost the same rate. So at some point there's some kind of intricate, if you like, self-regulation between creating new fragments and merging the fragments away. A little bit what we saw here in this movie on the left side. And at some point, with time, after a few 10,000 years, when the protostellar evolution eventually stops, then there is some kind of a self-regulation. It's a kind of a steady state equilibrium. We have new fragments, we create them, we destroy them, but in the end, we end up with a handful, maybe up to 10 fragments. So this is a typical level of complexity, multiplicity of population 3 stellar systems that form in a mini halo. So a handful, maybe up to a 10. And again, that is sort of a pretty well agreed. The only problem is that this plot here that was put together by Shingo Hirano, this plot goes to 100,000 years. So this is sort of the time frame that we want to push the understanding of population 3 star formation and the protostellar disk dynamics. The only problem is this is really a semi-analytic extrapolation. It's not possible yet to simulate all the way there, because this simulation that Thomas Greif did 10 years ago was incredibly expensive. It's still very expensive, and back then with the supercomputing, this could be pushed to 10 years, and now this can be pushed to a few hundred years, maybe 1,000 years. But we are still not there at the end game, because this is incredibly if you want to resolve individual protostars and the dynamics, it's very, very computationally expensive. And what adds to the computational challenge even more is the second frontier. This is the radiative feedback. So at some point, when and this is again what is shown here is the center of a mini halo, and in the very center of the mini halo we have a population 3 star. If you look very closely, you may be able to see this this white symbol. This is the first population 3 protostar that forms, and then after a few thousand years it reaches 10 solar masses or so. And at that point, the protostar is able to produce ionizing UV radiation. And then we begin to have a more and more increasingly vigorous radiative feedback. So what is shown here is the ionization fraction. So these yellow whitish bubbles, they are a bipolar hourglass emerging ultra compact H2 region, if you like. There's a photo ionization feedback, and these little arrows, they indicate the radiation pressure. So at some point, radiative feedback limits the amount of accretion onto individual protostars. And again, this now gets us into the regime of radiation hydro on top of the dynamics of this merging and fragmentation that we have seen before. So all of this together is computationally super challenging, and we are not quite there yet. But we can extrapolate. And if one extrapolates, then first schematically, right, in terms of the first star population 3 final initial mass function. So right, then schematically, right, we have something that we don't quite know what exactly the mathematical form is. Is it a Gaussian? Is it a shifted form of the locally observed IMF? That we cannot be sure. There's a question mark, but everyone agrees on that the characteristic typical mass of the first stars is shifted to a few times 10 solar masses. So this is interesting because this is right, the typical mass range for core collapse supernova. So the prediction is also that there is a range of masses. Right? We will have a few extensions to lower masses, higher masses, and then that's interesting because if we get to low masses, maybe even slightly below a solar mass, and in principle we could search for and make predictions for low mass survivors, low mass population 3 stars. Although right, in the Milky Way, we now have looked at the stellar archaeologists who do this, right? They have looked at millions of metal poor stars, and no one has ever found a completely metal-free population 3 star. So that might tell us that there is a cutoff here somewhere which is above 1 solar mass. But this is sort of right, one issue, and then there's also an extension to higher masses, and of course this gets interesting because at some point higher masses, of course, that gets us into the realm of black hole, right, stellar black hole remnants, maybe gamma ray burst progenitors, and then if you push this to the extreme, we also might be able to get into the regime of being able to trigger hyper energetic supernovae, pair instability supernova, which basically push the supernova explosion energies to the limit. And all of this, of course, right, the low mass survivors could be surveyed in the local Milky Way. We could also, this is one of the targets for the James Webb Space Telescope, and then afterwards, well, it used to be called WFIRST, now it's the Roman Space Telescope. 10 years in the future or so, right, we can also then look for these hyper-energetic pair instability supernovae. So this is schematic. And again, right, the agreement is we have a top-heavy initial mass function with right, the question of what exactly is going on with the mathematical form, but to also show you one actual output from the simulation. This is Athena Stacy's version. In this case, basically, right, there is an emerging power law, and then if we fit, right, if we fit a power law, then we get a power law slope that is really very, very flat, much flatter than what is observed for the standard saltpeter IMF. And the saltpeter IMF, right, as is well known, is bottom heavy. So right, star formation in the present day universe typically makes low mass stars like our sun. But then if we go to these kind of power law slopes, then we flip from bottom heavy to top heavy. And again, right, what exactly the functional form is and what exactly the power law slope is, this is debated, and that there's probably some cosmic variance also at play. But I mean, power law slopes like this, you will see them quite frequently in the literature. Something like this is not unusual. So, right, the main message is here: the first stars. The prediction is they are top heavy, and of course that has implications for the way that the stars impact cosmic history and also for their observability. And we will get back to that in a moment. But just very briefly, let me also mention a second aspect, right? When we think about the properties of the first stars, population 3, we are really dealing with a completely unknown, observationally unconstrained stellar population. We know they must have existed because, right, the Big Bang nucleosynthesis provided only hydrogen helium. So we have to get star formation going with these unusual conditions. But right, we have at this point no direct observation. So we really are out there in the right without a safety net. So these are really yeah, we have to try to constrain the properties of an unknown population, POP3, and we have right some ideas from these simulations, cosmological initial conditions, pushing into the radiation hydrodynamics regime. So we know something about the masses, and at some point, understanding the masses of the first star is, of course, the most important aspect. But you also, right, at some point, want to know things like rotation, because, right, when we think about rotation, it's really super important for things like chemical mixing, mixing currents and rapidly rotating stars. They will greatly impact the way that the first stars, population 3 stars, will evolve. And I saw on your Quid Ultra speaker roster, I think a bit later this semester, you will have Georges Menet from Geneva speaking on this topic, and I believe he will say much more about the beautiful role and the important role played by rotation. And then also rotation is super important for predicting the way that the first stars would die. What is their death? For example, if you want to understand the rate of high redshift gamma rebirth, then there's the idea we need to have a collapsar. Collapsar is a black hole, massive black hole, and then there is an accretion torus around, and to have this setup, which then triggers a relativistic outflow, we need material with high angular momentum. So rotation is important for all of this. Just to mention, the understanding of rotation of the first star is much less developed than our understanding of the mass distribution of the first stars. But there's some baseline understanding that at least a fraction of the first stars were rotating really very rapidly. So if you just sort of look at this plot here, which shows the rotation speed on the surface of the star versus time. And at first, let's look at this black curve. The black curve shows the situation if we do not have any magnetic fields, any MHD effects. And then the prediction there is that very rapidly, the first stars, if there's no interference from magnetic fields, will reach rotation speeds close to breakup. So that is, again, it's a first order prediction, but the first order prediction is if we can ignore magnetic fields, the first star should rotate rapidly. But then also, this is sort of, again, Shingo Hirano and I, we try to look into this in this very, very simplified way. This is one of the other frontiers of introducing magnetohydrodynamic effects into first star formation, in particular what MHD torques, magnetic fields do in terms of transporting matter and angular momentum in these protostellar primordial disks. So then, we have a tricky MHD problem of transporting angular momentum. And again, just to give a schematic example of what might happen is if we have magnetic fields, they might get rapidly accelerated in these primordial disks because of dynamos. And again, the details are messy and we don't have time to discuss them here. But if we have such an MHD scenario, then we would have the situation that's here shown by this red line, that then eventually magnetic torques really would act to rapidly break the rotation speed. So maybe we have a bifurcation into slow and rapid rotators. At what ratios, we don't know. But again, this is just as a quick note. We want to understand the initial mass function of the first stars, absolutely, but there are also other aspects of rotation and then also binarity, multiplicity. But let's at this point move on and think about what happens. If we have this setup that we have this almost universally agreed prediction that the first stars were typically very massive, had masses in the progenitor range for core collapse supernovae. So then the implication is that then very rapidly after the formation of the first stars, short lifetimes, few million years, we will get into the regime of supernova feedback. Just one example, in this case, this is sort of this yellow line here is a mini halo. In the middle, there is, in this case, 40 solar mass star. The 40 solar mass star then dies as a core collapse supernova. And this is simulated with an adaptive mesh refinement code. Then the supernova begins to mess up, destroy largely this is the gas distribution, this is the temperature, so there's vigorous feedback. And most important for our purpose is this plot. So again, this black circle is the virial radius of the mini halo, and this is the metallicity of the halo and the environment. And white means zero metal, zero heavy element content, so pure hydrogen helium. And then we have this color coding of enrichment with the elements that were synthesized in the core collapse supernova. And then this is really interesting in terms of hydrodynamics. This is right? There's turbulent hydrodynamics, shocks, dissipation of energy. But the important aspect is that a fraction of the metals, they make it out of the virial radius of the mini halo into the intergalactic medium, and another fraction of the metals, they are confined in the mini halo themselves. But the important thing is that very rapidly, right, we have metal enrichment kicking in, and this then very quickly completely changes the way that star formation happens, galaxy formation happens in the early universe. And but one way to look at this is, and this is now a cosmological simulation, 4 megaparsec, and 4 megaparsec may not sound much for boxes that right, people consider for lower redshift when right, we want to understand reionization or subsequent structure formation. But at very high redshift, right, redshifts of 10 or so, up to redshift of 10 or higher, 4 megaparsec is actually a representative region of the universe. And again, this shows the metal content of the universe at this time. And white again means no metals, no enrichment, pure hydrogen, helium, and then we have these islands of metallicity. And when you look at this, there are two messages. First, well, large volumes of the intergalactic medium, they remain pristine, and in principle, right, we may be able to eventually probe them with next generation quasar absorption studies, the low column density Lyman alpha forest. But at this point, right, we cannot be sure whether this is really right, whether we have these large volumes of metal-free gas, but that's the prediction. But then, again, for our purpose, first star galaxy formation, right, we see this rapid enrichment to quite high levels. And then in the sort of the levels that are reached are at 1% solar, 10% solar. Although the volume fraction that is affected by these bubbles of early enrichment, the volume fraction may be low, but these bubbles, they form where the cosmic density is high, where in a way all the important things, all the action happens, because like this is sort of those are the formation sites for the first stars and galaxies. And then the message is that we have metal enrichment very quickly, and this metal enrichment from POP3 star formation is quickly hidden by all the subsequent activity, then second generation stars, population 2 stars, third generation stars, fourth generation stars. So the universe is rapidly being transformed from the initial primordial hydrogen helium into a highly enriched state, at least in the high density regions. And one other way to see this, and this is really an important part of the message, also when we think, right, what to expect with the frontier observations from the James Webb Space Telescopes and eventually the extremely large telescopes on the ground. So this is the star formation rate density as a function of redshift. So this is early times, and then time flows in this direction. And first, let's look at this blue curve here. The blue curve shows the star formation rate density of metal-free stars, population 3 stars. So at some point, right, it starts redshift 30, 20, right? Where exactly it starts depends a bit on cosmic variance, but something like this is typical. And then, right, there's sort of some ongoing level of population 3 star formation in mini halos, right, throughout the history of the universe. But I mean, at some point up to redshifts of, in this case, we go up to redshift of 8. And then right, at some point it will come to an end. But the important point here is if you now look at what happens with this orange curve, this shows the star formation rate density of population 2 stars, metal enriched second generation stars. And then right, we see that very rapidly the orange line intersects and then basically becomes dominant by more than an order of magnitude over population 3. So the picture here is that the universe is dominated by population 2 metal enriched star formation very early on. And that also means that right, it will be very difficult to sort of disentangle the needle in a haystack. Sort of this right, baseline here of low level population 3 star formation is right, will be hidden in this huge haystack dominating component of metal enriched star formation. And this prediction that we have this transition between population 3 to population 2 very early in cosmic history is generic. That is sort of a part of lambda cold dark matter. To change this, right, one has to do something dramatic to the properties of dark matter. And at the end of the talk, I will briefly mention some possibilities. But this is really one of the main predictions for the James Webb Space Telescope. And to see this more clearly, let me phrase this slightly differently. So right, when we think about cosmic history, schematically, right, time flows in this direction. Redshift 20, we start with the formation of the first stars in these dark matter mini halos. Then we have supernova feedback, and then right, the second generation stars, they form in systems that have total masses, right, maybe just 10 to the 8 solar masses, and this is then where right, where the second generation of stars form, already metal enriched population 2 stars. Just to sort of show you that even right when we go, this is sort of the very beginning of star and galaxy formation in cosmic history. So this is sort of the simplest setup that you can contemplate, right? The simplest setup for star formation, the simplest setup for galaxy formation. But then even if we do this, right, the simplest setup for formation of the first galaxies, we already are dealing with considerable complexity. And just to show this, this was a simulation done by my former student Myung-Wong John, who is now a faculty member in Korea and Seoul. So this is dark matter, the large-scale context, and sort of this little white dashed circle is the visual radius of the emerging first galaxy. There's a 10 to the 8 solar mass first galaxy. And then this would be gas density, this would be temperature, so there's feedback. But the important thing again is sort of this panel here. This panel again shows the metal enrichment. And now, I apologize for that, the convention is different. Now black means no metal enrichment. Black means pure hydrogen helium, and then right, greenish and reddish means increasing enrichment with metals. And again, then right inside the emerging first galaxy, this is important, right? We have already a significant bedrock of metal enrichment, and then right, if one looks at this, is sort of about percent solar. So already, right, the first time that the universe has the chance to form a galaxy, right, there's metal enrichment. So there's this ubiquitous, if you like, metallicity flaw. And the prediction is generically, if we work with the lambda CDM cosmology, that the first galaxies are predominantly population 2 systems. And this will be seen by the JWST. But also to just bring back the point that right, the first galaxies already, they are quite complex. So if you now go from here and then we zoom in, right, inside what happens inside this system. So then here, right, this is sort of the gas density, but also we mark the individual remnants. So they are population 3 remnants. They are population 3 neutron stars, population 3 black holes, and the white here, those are then population 2 stellar clusters. So already, right, the very first time that the universe has the chance to build a galaxy, this is quite messy. And in terms of observability with the James Webb Space Telescope, so if you think about right, star formation rate, right, solar mass per year, then right, time flows in this direction, then the progenitor of one of those galaxies that we have just looked at, it all starts with mini halo formation, right? This is where million solar mass mini halos are where we have the first stars. And there's a little bit of feedback, there's a little bit of suppression, right? There's some episodic star formation, but eventually when the galaxy grows, the mass of the host dark matter halo increases, we go from this episodic regime to self-regulated star formation. And also then, if we basically ask ourselves, what does this mean in terms of right, the flux of the stellar population, the observed flux? So this is sort of UV flux, nanojanskis, right, following the system. And at first, right, there's very, very little. Right, these lines, these horizontal lines, they are thresholds for the near come. So right, 10,000 second, 100,000 second, right, million seconds, of course, right. This is really pushing it. This would be an extremely deep field, maybe lensing assisted, but eventually, right, we will cross into the into the observability. And this happens typically at about a redshift of 15 or so for the kind of systems that we have looked at earlier. And then what kind of spectral energy distribution would we expect? So there's of course a continuum, there's a UV continuum, but then for these first galaxies, we also expect a very strong contribution from nebula emission. So they are strong nebula emission hydrogen lines, and it turns out that for these systems, the strongest emission line actually is the H alpha nebula line. So then, if we want to detect the very first galaxies, we would have to hope to pick out these emission lines. But it's clearly sort of the observability is such that we really probably also need a boost from lensing boost, something that happened for Hubble with the Hubble frontier fields. But then to just wrap this up, the UV luminosity function of the first galaxy. And this is one of the main targets for the first year or two of what the JWST will provide. So this is a messy plot. So I try to walk you through this. So this is sort of different redshifts, redshift 8, 10, 15, and at redshifts 8 and even 10, there are considerable observations from the Hubble Space Telescope, sort of these symbols with the error bars. But just for simplicity, let us sort of focus on what happens at redshift 15 here. So redshift 15, in luminosity functions, so we plot a number of galaxies as a function of, in this case, absolute magnitude. So these are very low luminosity things. These are bright things. And at redshift 15, well, there are no direct observations yet. So these are all theoretical predictions, the symbols, and I will tell you in a moment what they are. And they are extrapolations. These lines are extrapolations of the luminosity function, the observed luminosity function at lower redshift. So this would be this dashed line is an extrapolation, a Schechter extrapolation technically. But the important thing is that there are two kinds of sources. There are these orange little symbols, and the orange symbols, they are dominated by population 2 stars. And then we can also, in principle, there are some systems that are only they are only powered. The emission is only powered by population 3 stars. So we would call them POP3 only galaxies. And they are here marked by these bluish Roman 3 symbols. So those are population 3 systems, and these are population 2 systems. And then the message here is, well, yes, there are these pure population 3 systems, but they are beyond the observability even of the JWST, even if we put in a lensing boost. So the prediction is that the ultra deep fields of the JWST that we will see, will see metal enriched galaxies. But again, that is a prediction, because that only is the case if we work with a lambda CDM cosmology. If we have different kind of dark matter, this will be different, and the enrichment might be delayed and all of this. So this is a prediction from lambda CDM, and we really have to see what reality is like. And I will sort of get back at the very end in a few minutes to what happens when we change the assumptions on the dark matter. Okay, so just to push this forward, now we have one of these first galaxies, 10 to the 8 solar masses, what's sometimes called an atomic cooling halo, redshift 15. And in this case, we assume this is pre-enriched to 1% solar, and then this is a simulation that now uses again an AMR, a flash AMR simulation, to zoom in and see what happens to the gas density. So this is gas density. Yellow is high density, and then if we zoom into the center of a first galaxy, then this shows the star formation process happening. And then what is visible here is we have the organization of this enriched gas at a level of 1% solar, into this is supersonic hydrodynamics. There are shocks, there are filaments, and the filaments become unstable and then fragment. So this is, in a way, it looks quite similar to what we would see in a Milky Way, a giant molecular cloud. Supersonic, turbulent dynamics. And then at some point we get to the stage, these little symbols here, where we pause the simulation for a bit, where we have 1,000 solar mass or so, right, which again we could call in the language of present-day star formation a pre-stellar clump. And then we can zoom in, and then we go and get to the point of individual protostars. These little symbols are individual protostars all the way to the opacity limit, meaning we have a hydrostatic core. And then in this case, there are a few tens of these stars, and then we can count. We can create a histogram, and the histogram is shown here. Number of these protostars as a function of mass. And let's not worry about the difference between blue and red. They are doesn't really matter here. But then we have a histogram, and then we can fit a power law, and the power law that we fit here is not inconsistent with the standard salpeter value. So what that means is that before that, when we started with population 3, the first time the universe formed stars, we have a different IMF, a top-heavy IMF, very different from present-day star formation. But now, the second time, I just showed you a movie that shows the second time that the universe has a chance to form stars, and slightly metal-enriched gas, and then already we are back to something that looks like almost the standard salpeter IMF. So the message is the universe is very quickly, although it starts with exotic star formation processes in the POP3 systems, the universe very rapidly transitions back to star formation that then is universally, almost universally observable for the rest of the history of the universe. That is really quite remarkable, how quickly this transition happens from POP3 to more normal star formation. If you now push this forward, then there's one other really interesting aspect, and this is sometimes called stellar archaeology. And the idea is that we now look at the local group, and this is a box that's again a simulation done by Myung-Wong John. This is here the dark matter, which shows a situation that is somewhat similar to our own local group. There's a massive galaxy, and then there are these little tiny satellites, and they are dwarf satellites, and then we can zoom in, and then we can really with high precision see what happens inside those dwarf galaxies. And in this case, what Myung-Wong did is she really then did a simulation where she traced the star formation and metal enrichment from individual populations 3 and 2 stars, and then she pushed it to redshift 0 so that we then can see what we get in terms of observation. The message then that comes out is that we can make predictions, and Myung-Wong then made these abundance plots, the carbon abundance, the alpha element abundance, and the details here don't matter so much, but basically the individual symbols, they are individual stars, predictions for individual stars, and then in principle one can begin to compare them with observations. So this is a very, very high precision way to do to do near field cosmology, and the assumptions on POP3 star formation that are put into these simulations, they then are reflected in these abundance patterns. And just to make one, the most famous maybe of these abundance patterns, in a little bit more detail, is the carbon abundance. There's a famous phenomenon in stellar archaeology when we look at metal poor stars, and then here we plot the abundance of carbon, some measure, doesn't matter what it is, and then this is metallicity, iron abundance, and we go to really extremely low values of metallicity, and then the idea is there are two populations. There are stars that are normal, they are not enhanced in carbon, and then there are very, very intriguing stars that are highly enhanced in the carbon abundance, and there is a convincing story how this might come about. There's a peculiar kind of a supernova. If you have supernovae that are massive enough so that they will create and die as a black hole, then this could lead to what's sometimes called a faint supernova. So the idea is all the heavy elements, iron peak, also probably most of the alpha elements, they are gobbled up, they are eaten up by the remnant, by by the black hole, but only the light elements that are created in the envelope, right? Say carbon, oxygen, maybe nitrogen, right? They are making it out. So the idea is, right, if we have these population 3 stars that are massive enough to hide, if you like, most of the heavy chemical elements in the remnant, in the central remnant, then, right, we have a mechanism to understand why would the first stars typically lead to highly carbon enhanced stars. And then just to show one example, this now shows the situation in the Milky Way halo. So this is right. There are predictions. The predictions are these blue symbols and the red symbols. Blue symbols are right, stars that are enriched by population 2, and the blue symbols, they are enriched by population 3 stars. And then, right, what is really interesting is that right, the population 3 enrichment, this is a possible explanation for what's observed in the Milky Way. Right? There is sort of this group of highly carbon enhanced stars. And then, right, it seems that one can really make the case that these extreme CMP stars, carbon enhanced metal poor stars, these extreme CMP stars, they are really right, a fossil remnant of population 3 nuclear synthesis. That is really interesting, and of course this is something that will become much more important in the future when we have the extremely large telescopes. So I'm almost at the end. Just to also show this, right, another way is to look at gravitational waves, and of course, right, this is super exciting, right? It's an exploding field. We have the right, the LIGO Virgo database of black hole, right? And of course, this is just a small subsample. Right? We now have hundreds of sources, and we will soon have many more. And right, there's a distribution of masses that then merge. But also, what has emerged is an interesting class of merging events, and the most famous may have been the right, GW 190521. This is a system that creates a really massive merging product, but maybe even more importantly, the progenitors already that are inferred from the LIGO Virgo analysis. Right, the progenitors are so massive, more massive than 60 solar masses, that it's not easy to explain right, how we get those progenitors, because standard stellar evolutionary channels, they make this very difficult to have this kind of progenitors. And the reason is it's sometimes called the gap due to pair instability, electron-positron pair instability. But the point is, right, normal star formation, population 1 star formation, population 2 star formation has trouble explaining this, but with population 3, right, this was a paper written by my student Boyuan Liu. Right, one can argue that there is a way to explain these kind of systems quite naturally. And then, just to mention this is really something that is absolutely exciting. Right, so these gray lines, they are predictions for merging population 3 binary stars, right, in the gravitational strain versus frequency domain. So this is sort of in spiral. Then there's merger, and then there's ring down, and right, just there are all these sensitivity curves of future gravitational wave instruments, but just sort of, right, even if you look at this is LIGO O2, right, even LIGO already can pick out in principle, right, many of those merging population 3 sources potentially. And one can make the case, and right, Bojan and I, we have proposed this, that a few percent of the LIGO sample may actually have a population 3 origin. But just to say this, right, this is really interesting. And now the really final point, right, we have this connection to the property of dark matter. And dark matter, well, the standard assumption is cold dark matter is some kind of supersymmetric WIMP, weakly interacting massive particles. But then the problem is, right, if we look at the parameter space, say the cross section, how WIMP dark matter might interact with nucleons as a function of WIMP mass, right? Sort of there is a region that is ruled out by current limits, and this becomes more and more dramatic. So at some point, right, the WIMP may simply not exist, and then really we are in a situation where there may be a conceptual crisis from the particle physics viewpoint, because then we really don't know, if we don't have supersymmetric WIMPs, and what are we dealing with? And maybe even we have a completely dark sector, so that the dark matter is completely disconnected from the standard model other than gravity. And if that is the case, then we only have astrophysical constraints to learn anything about the dark matter. So just to show one example, of course, then many different models are explored, but one particularly curious one is what's sometimes called fuzzy dark matter, FDM. Fuzzy dark matter is a very strange kind of dark matter. It's an ultralight particle. It's so light that it has a de Broglie quantum mechanical wavelength of galactic scales, of a kiloparsec scale. And kiloparsec, of course, this would be one way to explain, for example, why are there so few small dwarf satellite galaxies? Why are there things like central cores? So all of this, a kiloparsec scale is interesting. And also, of course, means larger galaxies with on radii of 10 kiloparsec, 100 kiloparsec, they will not be affected by this dynamics. But on small scales, we could then have a dramatically different picture. And just to illustrate this, if we have again the simple picture, cosmic time, redshift 20, we have mini halo dark matter, first stars, then second generation of stars, and so on. And then with fuzzy dark matter, the prediction would be that the first, because of this quantum mechanical pressure, this quantum mechanical destruction of small scale structure, all of this action, everything I have said in my talk until this point would not have existed. All of this wouldn't be the case. The first time that the universe would form stars would already be in a very massive galaxy. And this, of course, then would have dramatically different consequences for observations with even the JWST, because then all of this deep structure, this post-starburst structure wouldn't exist. And we would see galaxies, primordial galaxies that are born massive. The prediction now is that massive galaxies are already evolved and metal enriched. If we have fuzzy dark matter, JWST will see these massive primordial galaxies. That would be exciting, but also would be super, super weird. Yeah, just to, I think my time is almost up. So just to mention this, of course, you have all probably followed this exciting Christmas Day event, the final launch of the James Webb Space Telescope. I'm sure you all also have seen this unbelievably beautiful image, the final goodbye of the telescope. And as we know, it all worked incredibly well. The deployment, the telescope has arrived at Lagrange point 2. All the deployment steps have worked, and now for a few months, none of us, most of us, will hear anything. Probably then, May, June, then we will finally see the famous first image, which is a big secret what the Space Telescope Science Institute plans. And I have asked my colleague Steve Finkelstein, who is one of the major PIs of the Cycle 1, and he also doesn't know what the first image will be. But Steve Finkelstein also told me that data collection really will start in the summer, June, July, so then, the second half of this year, we will begin to see the James Webb Space Telescope really probing these this exciting period of first star galaxy formation, the end of the dark ages, yeah, that is really an incredibly exciting moment, because as I've said, we have had at least 20 years. Many of us, also in this in this virtual room, we have worked very hard to come up with a theoretical picture to understand the beginning of star and galaxy formation in the universe. And we really want to close this final gap in our worldview. We want to push the frontier to a few 100 million years after the Big Bang, when we have the entire star formation history of the universe in our reach. But at this point, it is a theoretical framework, a theoretical prediction. I think we all, who are on the theory side, I believe and have definitely tried as hard as we can. But it will be so very exciting to then see the real data with the James Webb Space Telescope. And again, what this is all about, what I think is unbelievably beautiful and will remain beautiful for at least the next decade and beyond, is this high redshift frontier that we, humanity, human beings, our brains are able to contemplate one of these very, very big questions of our existence. How did it all begin? And yeah, so I think this is very exciting, and I'm very happy that I had the chance to share some of my thoughts, reflections with you this afternoon. And then I think my time is really up. Thank you so much for your attention.
Thank you so much, Volker, for this incredibly beautiful and inspiring talk. A lot of work to be done in interpreting JWST data for the next 10 or 20 years. So I think I want to give the chance to people to ask questions. So is there any question from the audience? You can raise up your hand or switch on your mic directly if you want. So there was a question actually on the chat by Martin Topinka, who was asking whether the picture would change with black hole seeds. I think he was meaning relative to the prediction for the star formation rate density evolution, so the effects of black hole feedback. I don't know if you want to. You then touched it a little bit, but I don't know if you want to share your thoughts on the effects of early black hole feedback on star formation rate.
Yes. So I mean, black hole feedback is important, and I have said little about this because this really would be a separate talk. And of course, right, Rafaela's group and many of the students here, of course, right, you work on this, so of course you know this, right. This is really important, black hole feedback, and yes, I mean there will be changes, but of course I would say, right, probably not not qualitatively, in the sense, for example, that we would shift this sequence of right, we begin with POP3 at this rough level, and then we have a rapid transition to population 2. Of course, right, with the seeds, as many of you know, of course, there are two broad classes. They are the stellar seeds, right, 50 solar mass, 100 solar mass, plus the massive POP3 stars dying. At some point, right, those seeds, this black hole activity is inevitable, right? That is sort of a standard part of this picture that I have focused on. We have POP3 stars, we have a top-heavy IMF. We will have a significant portion, like 50%, what exactly, right? I mean, but maybe something like this 50% of the first stars will die as black holes. So we will have lots of this seeding activity from the stellar channel. Then, of course, the other question is, what about these direct collapse black holes, which probably also existed? We shortcut the beginning by not forming stars first. We have a primordial gas cloud that directly collapses into a more massive seed black hole. Maybe we start with 100,000 solar mass black hole. And of course, that's important for the question of then seeding quasar activity and all of this. But my take is that those more exotic DCBHs, I believe they exist, but they probably will be rare in terms of number density. So I think, right, it's absolutely, right, worthwhile and exciting, right, as one of the important targets for the JWST to look for the signature of DCBH seeding, and but in terms of really changing the overall cosmic star formation rate density, I don't think there would be an impact, but we have to see. Yeah. But yeah, in general, black hole feedback, absolutely important. And yeah, I'm sorry that I couldn't say more about this.
So there is another question from Martina Rossi. I don't know, Martina, you want to ask the question directly? You can switch on your mic and ask the question directly if you want. No? So I can read it for you. So CNP stars can be explained by core collapse POP3 supernovae, or faint POP3 supernovae are the only supernovae type that can produce high C/iron ratios.
Well, I mean, there are alternatives, and my guess is, right, when you will have the talk from Georges Menet, he may probably, right, mention some of this, and of course, right, also Rafaela, of course, your group has also worked on this. I mean, there are probably different channels, and of course, also I was not sufficiently precise. What I really was talking about is a subclass of the CEMP, carbon enhanced metal poor stars, which are sometimes called carbon CEMP no stars. Those are really stars that are enriched in carbon but don't have any R process elements. So it's this particular subclass is probably linked to POP3 progenitors, a supernova that is able to prevent the iron peak elements from escaping by gobbling them up in a black hole. But then, I mean, when it comes to CMP S stars, CMP R stars, of course, this is much more complicated. Then we have binary channels, I mean, yeah, one can explore other channels. But I think this idea for the CMP no stars, the connection to these black hole forming POP3 progenitors is compelling.
Yes, I agree completely. So is there any other question from the audience? If not, I take the chance of asking one. So you mentioned the difficulty of, for JWST to really look after this POP3 dominated systems at very high redshifts. So what is your opinion on the possibility to really disentangle some POP3 signatures in first galaxies instead? So in systems that would be likely very often used by JWST. So is there, given your experience in numerical simulations of these objects, is there any chance to really, disentangle some specific signatures in the spectra of these high redshift galaxies, mixed systems?
Yes, and that was, again, there I oversimplified in my talk. Of course, that's an important parameter, right? The mixing parameter, because we have probably some pure POP3 systems and maybe some pure POP2 systems, but at some point early on, there is a mixing of the two components. So there's this fraction, and at some point, if we have, say, 50% POP3 contribution, and then we have the aggregate SED, then this probably can be disentangled. I don't think we can disentangle a trace 5% or something. But say a hefty component can be disentangled. But I think that would have to happen spectroscopically, because the first observations will be photometry, right? We will see. We will have very limited information, broadband filters, and I would be surprised if we can really measure the broadband colors to the precision of disentangling some mixed 50-50 system even. But if we go into the spectroscopic follow-up, with then say the extremely large telescope, if we have spectroscopy, then of course we can do this in a much more powerful way. And at some point, yes, I think mixed systems, that may be actually what will happen eventually. We will see POP3 in these mixed systems.
Thank you. Yeah, so someone is asking for your slides, and I swear I will share the slides on the Quidultra webpage. So is there any other question for Volker or curiosity?
I have a curiosity, if I may.
Yes.
So since it's very difficult to disentangle POP3 and POP2 contributes in these early galaxies, is there any chance instead to have some constraints on POP3 formation history, and in particular on their episodic behavior, let's say from the 21 centimeter signal?
Yes, that is again one entire that's a very, very powerful diagnostic, and I didn't have time to touch on that, but that would be another a really interesting talk, and it's very powerful because yes, I mean with 21 centimeter cosmology, of course, there are right? They react to the underlying stellar population, and POP2, right, will impact the intergalactic medium in different ways from POP3. For example, right, even the production rate of Lyman alpha photons, right, which then would drive the Wauthausen field, or the bubble size, right, of the ionized radiation. So I mean, at some point, with the precision that we can reach with the SKA, right, in the future, indeed, I mean, right, one can begin to ask this question. Then, of course, also, right, the clustering signal will be different from POP3 systems versus POP3, right? POP3 is much more highly biased. So an SKA is a fantastic high precision tool. This is a bit like, right, the stellar archaeology at low redshift. With the 21 centimeter cosmology, we can do high precision, right, at high redshift, and then we can begin to disentangle these contributions. Absolutely.
Thank you.
Thank you, Volker. So I think we have to leave you to your work day now. So
maybe just sort of also one invitation to everyone, but in particular the students, because of course normally, of course, I understand, right, because then if I had visited, of course, then, right, there would be the way to communicate, right, with all of you, and to chat and to have informal. If at some point, right, over the next few days, right, any of you have any questions, my my inbox absolutely is open. Just drop me a note. I promise to respond, and I also promise that I will deliver my slides to Rafaela. But yeah, please don't hesitate. Right, I would be very happy to answer any questions that you have at a later point.
Thank you, Volker. Thank you so much, and thank you for having given us this wonderful review of the field. And yeah, I hope that we will celebrate the first JWST observations maybe together. Maybe we will share the emotion.
Indeed.
Okay.
Indeed.
So thank you so much, and thank you everybody for